All right, nice to see everybody's relaxed. I see Tsepo's eating an apple. It's good. All right, so the numbers are still filling in. All right, so I'm just going to start now, 100% with stay healthy. Okay, so I'm just going to start off just introducing what we're going to do today. So again, I just want to make sure I'm going to confirm. You can see my mouse cursor when I move it on the PDF. The question is, can I stream in a high resolution? I'm streaming in the highest resolution that I can. So I'm streaming at the moment in 720p. That's the maximum I can stream in. And already these files are getting big. So they are, what is about 400 megs a lecture. So they are getting sizey. I hope everybody can see. I will record it in any case in 720p. So that's definitely good enough quality to see what's going on. So it might be that the streaming that you get to on your side is not that great, but that the quality of the resolution quality that I will record in will be 720p. Okay, so that's definitely, and like Johannes mentioned, you can set your receive resolution. You can fix it as opposed to have it automatic. It might just cause some delay in streaming as we go on through the lectures. Okay, all right. So let me start off with what the whole aim of today's lecture is. So I'm going to start quite slowly today. I just want to make sure that we all catch up a little bit on some of our background. And the focus of today's lecture is really going to be just talking about statically determinate structures versus statically indeterminate structures. And today we're going to focus it on simple geometries. In the end, what we want to try and do today is just to make sure that we have a good understanding of what's going on and be able to differentiate sort of our past knowledge that we've done in MOW 227 versus how we're going to build on that knowledge in this course. So I know in MOW 227 you've done statically determinate structures and a little bit of statically indeterminate structures. I'm not sure how much of that you've done, but by discussions with Prof. Kok, it's been a fairly limited exposure that you've had with statically indeterminate structures. So again, the difference here really is whether you can solve the problem. In terms of when I talk about solve the problem, when you can solve, when you think about the classical structural mechanics approach that we've been following when we solve problems, is can we solve for the reaction forces and get an idea of what the stress state is of the structure based purely on the equilibrium equations? Or do I need additional information? And so if I need additional information to just determine what are the reaction forces, then automatically we're in a statically indeterminate scenario. Okay, so on the left-hand side, I've given some examples of statically determinate structures. So let's just quickly run through them, and then I'll go to the light board and we'll have a simple example that we'll expand on. And hopefully by the end, we'll conclude with a bit of Python. So that is the idea for today's lecture. Okay, so essentially when you look at the statically determinate structures here on the left-hand side, what we see is essentially, I've got sum of forces in the x direction, sum of forces in the y direction, and sum of moments that I can use to try and solve for equilibrium. If I look at this first structure here, essentially sum of forces in y direction is 0, sum of moments is also 0 because all these forces act in the line. And so I've got one equilibrium equation, but luckily I only have one unknown. So sum of forces in x, with that I can actually then equate what is the unknown reaction force, and I would find that the reaction force would be essentially negative 10 newtons, so it would act in that opposite direction. Okay, so that's essentially for this first one. And the second one, if I look at sum of forces in the x direction, there are no forces acting in the x direction, so that's just 0. So here I've got luckily sum of forces in the y direction and sum of moments around any point should be 0 if that thing is in static equilibrium. And essentially I can then, with those two equations of sum of forces in the y direction, sum of moments around any point, determine what is the unknown m and v. So that's not a problem. And similarly for this one, I've got sum of forces in the y direction and sum of moments around any point to resolve both the two unknowns, v1 and v2. Okay, so that's statically determinate. That's stuff that you are very comfortable with after you've completed MOW 227. On the right-hand side, I've got, it's called a statically indeterminate structure. And now I'm asking the question, let's look at this first example. So on the left-hand side, we've applied a load, but on the right-hand side here, we're going to say, what if I take this bar and I pull it, that right edge, I displace by 0.1 millimeters. And now I'm asking, what is the reaction force on that left-hand side? And hopefully all of you would be able to be quite comfortable with the idea that if you made this bar, let's say out of toilet paper, it would be quite easy to do. But if you made this bar out of titanium, it would be a fair amount of effort to try and achieve that, depending on what the length of the bar is. But we'll get to that. But essentially, that's going to be influenced by what is this bar made of, the material that it's made of. So I need additional information. I can't answer this question without invoking some knowledge about the material as well. On the left-hand side, no knowledge about the material was necessary to solve the reaction forces or understand what the stress state looked like. But on the right-hand side here, it's really critical to understand what it's made of, because that will dictate really what is the forces on the inside. So taking a very simple example problem, just changing how I load the structure as opposed to putting a loading in, but rather giving a prescribed displacement, all of a sudden material matters and plays a big role in what the stress state looks like. Okay. If I look essentially here on the second figure here, this one, if you look at how many unknowns we have sum of moments and a reaction force V1. Then there's another force, reaction force here, V2. So I essentially have three unknowns. Sum of forces in the x direction is not going to help. It's just going to tell me 0 is equal to 0. So I've got two equilibrium equations. Sum of forces in the y direction and sum of moments. But with that, I can't resolve three reactions. And so essentially, for me to be able to solve this problem, I'm also going to have to know something more about what's going on in the problem in terms of some displacements or some additional information. I'm not going to be able to do it just purely from the equilibrium equations. And then this last example is also another clear example where we essentially have, again, only two equilibrium equations that we can invoke, sum of forces in y and sum of moments around a point. But then essentially I need to solve for four unknowns, which is not something I can do uniquely. Okay, so essentially what it means is I've got too much freedom, but the reality is the structure is loaded and it's deflecting. When you look at the structure in real life, it's got in a certain state, there's a certain kind of loading on that structure. And so what we are realizing is we just don't have enough information to tell you what is really the reaction forces here. So that's the issue that we have. Okay, so that's really the difference between statically determinate and statically indeterminate structures. And then I'm just going to quickly switch to the light board so we can take this further. Okay, so I hope I've given everybody sort of a clear picture of at least that part. So I hope the light board is clear. Let's make sure everything is reflecting again the right side. Can everybody read that? It's not inverted? Yeah, sure. Okay, that's good. Okay. So let's start off with this example problem that we had initially, the statically determinate example of just pulling a bar with a loading P. So essentially, here I've got a bar. Let's say here's my x-axis, so I can just define that nicely. That is essentially clamped on the left-hand side, and I'm pulling it with the force P on the right-hand side. So let's say the material of this bar is made of a Young's modulus of E. The area of this bar, cross-sectional area of this bar is A. Say the bar's got a certain length. So we're just giving it a lot of information that we have about the problem. And when I apply a load to that bar, so this is now essentially the bar in the underformed state. Let me just write here. So this is in the underformed state. Just going to recap a little bit of what we've learned so far about these things in our different courses. And if I apply the loading to that bar, essentially that bar will elongate under tension. And so we can say that that is maybe sort of the displacement that we've had. Let's call it delta. If I apply load P to this bar, it's being pulled in tension, and I can think of this as now essentially my deformed state. And I can maybe just draw it like this. And if you think about it from a two-dimensional point of view, there's going to be some Poisson's contraction, depending on what I do with the clamping. If it's fully clamped, then obviously the bar there at the edges would stay there, but it would then Poisson's effect would pull in. If I essentially put it under a loading that is like this with rollers here, then essentially that bar is free to contract and it will give us a uniform stress state. But that stuff it will detail that we get later into. For now, we're going to make the assumption that we only track what's going on in the one direction. So I'm not going to complicate this situation here by having different variations of boundary conditions there. We're really just going to be looking at how does things move in the x direction. How does the thing elongate? Okay, so let's just think of it for that for now. But I just wanted to remind you that in essence, although we simplify the problem to a one-dimensional state, that initially there's going to be the Poisson's effects that will kick in, but we'll get to that later in the course. Okay, so that hopefully gives us an idea of this is the deformed state. So what brings me, how do I come from this state towards this state? It's essentially how things display. So if I ask myself, what is the displacement, look at every point on this bar. If I have a couple of tickers on this bar and I ask myself, how did this point displace versus where it was to where it is now? Then I can get an idea of how the displacement would look. So let's say this is my u, a function of x, which is just u I'm going to use to talk about displacement for now. So that's my displacement of this bar. Okay, so u of x is how much this bar is displaced. If I ask myself, this point that's clamped here on this left-hand edge, how much did it displace from where it was? It didn't displace at all. If I ask myself this point here, the right-hand edge, which is at x equals to L, so that is at x equals to L, so this is x equals to 0. And I ask myself, how much did this displace? So I say, okay, so this point essentially displaced that much. So it displaced the amount of delta. And because we're busy with linear elasticity, linear materials, if I'm in the middle of the bar and I ask myself what happened to this point here, if this is the middle, let's say this is L over 2, here this is x equals to L. What happened to that point in L over 2? Well, it would have displaced essentially delta over 2. And so what I can say is that's now at x equals to L over 2. I can say this is essentially how the displacement of that bar would look for every point in that bar. So I've got now a field description for that. I can say u as a function of x is essentially something that is a function with a slope. So let's ask ourselves what this slope would be. The slope would be essentially this delta y over delta x. So that'll be delta over L. And then as a function of x, if x is 0, I need to have 0 displacement. If x is equals to L, I need to have delta displacement, and that's what it will give to me. So there's essentially a displacement field that I've got of the problem. Just talking about the problem, deriving it from understanding that points in this bar which is going to displace. And again, I'm going to remind you that in this course, we're going to be approximating fields and functions. And here's an example of a field that we're going to be approximating. Here's a displacement field that essentially we would like to approximate later on in this course. So u of x is equal to delta L over x. Okay, so that's essentially just to make sure that we run through the problem with an understanding about, again, the quantities like loadings that we apply, the material, and the fact that once it gets to displacement, then essentially there's some additional knowledge required. I need to know how the structure is going to be displacing. So how do I know this delta? How do I get this information? So let's just run through this problem from beginning. Let's first solve maybe for the stress state, and then we can take the stress state related back to strain, and then from strain back to displacement. So at the moment, I've given you and told you that the structure is displacing delta if I've measured that, and then from that we can actually guess a sort of displacement field for this structure. I could also just run it from the classical MOW 227 point of view, where we would have first solved for the structure. So, okay, so if I take this structure and I get its free body diagram, where I apply loading P, and I've got some reaction force, call it reaction force X. And if I want to solve now for what's going on in terms of the reaction force, I can say sum of forces in the x direction is equal to R of x plus P must be equals to 0. And from that, we know that essentially P is equals to minus R of x. So what we know is that the reaction force is pointing in that direction. And I just want to again put my x-axis here for clarity. So it's just clear. Okay, so that's essentially what we have. And now, once I have that, once I know what is essentially the sort of reaction forces in the system, and I know what is the predominant force. The force is essentially, if I make a cut anywhere in the structure, that force acting on that surface is essentially going to be B. Okay, so that's essentially, we have a nice state here. Now I can go and say, okay, what is essentially the stress in the structure? Well, we know that the stress is just the force over the cross-sectional area. So we have a loading P applied. And we'll get into stress a little bit later in terms of when it's positive and negative in terms of tensile and compression, but at least this structure I know I'm pulling, it's under tensile, so I'll expect to see a tensile, a positive stress state. And essentially the cross-sectional area was given to us as A. That's what we started off with. But we also know that this is essentially related to the strain in the structure via the material. So, and the strain is just telling us something about how the displacements relative, 2 points relative in the displacement field changes with respect to each other. So I just want to make a good distinction today between strain and displacement, that we just have clarity, because it's unfortunately something that's crept in the past to be sort of a problem. But I'll just clarify again from what you've done in MOW227. So this is essentially the slope of this is telling us something about the strain. Okay, so let's just go through a thought experiment before we continue, where I can just clarify quickly the difference between displacement and strain, so that we just have good clarity, good difference here. Okay, so the algebraic way to think of it is the derivative of the displacement is strain. But let's just think about it physically, practically, that we just have something as a fallback, that we have good understanding of what's going on. So if I have a bar, okay, so there's my bar. And essentially, if I move this bar, so there's the total length of the bar after I've done something to the bar, it's L. And all I've done is I've just shifted the bar, but it still stays a length of L. So it's moved. So the bar has definitely shifted, it's moved. There was a displacement applied to the bar, but the length did not change of that bar. Okay, so that is one scenario that I have. And this is what we will call a rigid body motion. And it's the same as if I take this Koki and I say, here's the Koki, and then, okay, let's translate it to the side. And now the Koki is there. So take something and translate it to the side to get the updated state. So how does this displacement field look for this situation of rigid body motion? So if I think of U of X, and let's say I displaced it by delta, but this is also delta. So every point, this point displaced by delta, this point displaced by delta, every point displaced by the amount of delta. So essentially my function is just delta. In that case, for the rigid body motion, that is the displacement of this from here to here. And did it take effort to do that? Did I feel muscles burning? Is it going to make a difference what kind of material I've made it of if I do this in terms of strain energy? No. So essentially, this required zero work from my side in terms of from a strain energy point of view, because I just moved the object around, but there was no essential stretching happening, so there was no effort required. If I go and I take the same bar, also the length of L, and I say, this point here stays the same place, but now this bar essentially elongates this one. So let's say this point that was originally here moved now that amount, delta. But this side stayed there. So essentially this bar is now it's got a length of L plus delta in total after it's been deformed. It's got a length of L plus delta, the deformed state of that. And that would have required quite a bit of effort depending on what the delta is. So if it was essentially made of titanium or toilet paper, it would have required different amounts of effort. Okay. So what we do understand here is essentially it's not the displacement that matters in terms of what the stress inside in the bar is. It's not the amount of the displacement, but what it is essentially what was the displacement between two adjacent points. So here, any two adjacent points, the distance stayed fixed, delta. Any two adjacent points, the distance before and after stayed fixed. Doesn't matter what I call it, what number it was. If this was the distance here, after I've applied my displacement, that distance stayed unchanged. There was a distance here, after I've applied my displacement, that distance stayed unchanged. That's why I don't require any effort. But what we see here is essentially, if I had 2 points here, and if I look after it's now been formed, those 2 points are not the same distance. They are now further away from each other. So a point that was essentially here and maybe here is essentially now, instead of there, is now further away, maybe there. And it's that kind of stretch that's happening that's causing us to store strain energy into that system. Okay, it's the same if I take a spring and I just move it around versus I take a spring and I stretch it, which requires some work and effort. You feel it in your fingers. Okay, so that is essentially what we have. And all that strain is that quantity that engineers have figured out that is related to stress by the material. So essentially, strain is a quantity that we have that sort of stretch or that relative displacement between 2 points on the structure that's telling us what is sort of the stress state in that structure. And it's related essentially via the material. So that is essentially the sort of slope that we have there. Okay, so that is just to make sure that we have again a reminder of a clear difference between displacement and strain. They're not the same thing. And the algebraic way of thinking about it is, in this 1D kind of case, is that the displacement's derivative is strain. But also from a understanding point of view, what it means is it really tells us something about what is the displacement of two adjacent points. Did they move the same amount before and after I displaced the structure, or did they actually move relative to each other? Because that then will essentially tell us that there's going to be some stress. Okay, so I hope that's clear, and I hope that's giving you, again, just a reminder of the differences between stress and strain. Okay, so it brings us back here. So let me just wipe this off. So I'm going to use this right now again. So that will hopefully just make sure that we have that as a point of understanding. Okay. So what we have is stress now. We have essentially the Young's modulus and this quantity, which is now the strain or strain x, depending on how, if you want to have subset notation. I'm going to just simplify it and just call it epsilon for now. And that I know is essentially E is equal to what was the sort of that total bar, the displacement of the tip versus the total length of the bar. And that is my indicator of my linearized strain. Okay, so that is my quantity for strain. And if I have this, then I can now focus on this part of the equation, and I can focus on this part of the equation to get an idea of how the forces and how the displacements in this bar would change. So I can isolate for P here and say P is equal to times with the A to that side, EA over L times delta. And let's just make sure that the units all work out. The units of delta is meters. The units of E is Newton meter squared, so it's Pascal. This is area, it's meter squared, so that cancels, it's just Newton. That's remaining in the top there. This length again is, the units of that length is M, is meters, so this is essentially Newtons per meter. So it's a stiffness. It's essentially the same as a spring. So that's what it simplifies to. And if I have Newton per meter times by meters or something, then I'll get something that is just the units of Newton. So everything is nice and consistent. And that is just to make sure that we have good clarity. Okay, so let me just isolate this equation. That we just have that. Okay, I can isolate for P and think about what the equation means. Or I can go and say, okay, let's isolate for delta and see what we learn from that. Make sure this is clear. So I can say it's PL over EI. Okay, and so essentially, if I apply a specific load to the structure of length L, made of material E, cross-sectional area of A, it will displace, the tip will displace by essentially delta. So that's essentially what we learned from this. So let's just make sure it makes logical sense before we continue on. If I keep the force the same in this scenario, I keep the loading that I apply exactly the same, I keep the length the same, but I make it from a stiffer material. So this, instead of making it from toilet paper, I'm making it from titanium. And if I apply the same loading, I expect, and I keep the cross-sectional area the same, I expect essentially the displacement to be less. Is that clear? So if this number is bigger, then essentially the displacement is going to be less. That makes sense. If I keep the material the same, so if I have toilet paper, but instead of just one piece of toilet paper, for instance, I have a whole toilet roll of toilet paper. So I make the cross-sectional area a lot more. The material stays the same, the length stays the same, but now I'm pulling on the whole toilet roll with the same amount of force. I expect to see less displacement. That's exactly what I see. So divide by a larger area of the same length material and the same material type, then all of a sudden displacement is going to be less. Okay, so that these two are nice, make logical and sanity check. And in essence, if I have a situation where I have the toilet roll, remember, this is what this delta is essentially. It's that tip displacement that we have. So about how much this is going to be displacing. So instead of having one toilet roll, I have a long toilet roll, and then I pull on that with the same force. I expect that tip to displace even more now, because remember what strain was. The strain is essentially the relative displacement of two adjacent points. And if these 2 points move slightly, and these 2 points also move slightly, and these 2 points also move slightly, the more of them I have that are displacing relative to each other with a small amount. And if I have lots and lots and lots more, then the total displacement is just going to add up to be more. Okay, so that's essentially, if I have a longer toilet roll, the same cross-sectional area, same material, under the same loading, I'll have a larger tip displacement. So all of this makes nice and sense, and it's important that we can think and reason about this, that we have good sanity checks, that these things make sense to us, because this is how we protect ourselves as engineers, is that we have sort of an expectation and make sure what we see indeed follows that expectation. Okay, so another, if you want to think of it not from the displacement point of view, but just from a stiffness point of view, what we can see is if I make the structure from a material that is essentially of a higher Young's modulus, it's going to be stiffer. If I make it from a larger cross-sectional area of the material, it's going to be stiffer. If I make that structure essentially longer, then essentially it's going to behave as if it's slightly less stiff. Okay, so that's essentially what it will be if I think it from a stiffness kind of point of view. But these two kind of arguments tells us quite a bit about what we want to know to make sure that we have good understanding just from the statically determinate case, the simplest case that we can do and that we can think of. Okay, so that's by far the simplest case. If I sit with this idea that I have strain, so this is now derived from starting off with the reaction forces being solved and knowing that we have now a tensile kind of condition here, seeing what the stress is, getting the stress related to the strain. I can now also go from this point of view and go and calculate what is the displacement field. Remember, we argued about the displacement field based on pure kind of logic, just from observing, watching what was going on. I can also now, just from doing my calculation complete, and say, so from this argument, du dx is essentially delta over L. So that's essentially what I have there. And now I can say, okay, so let's rewrite this so that we can integrate it. So u, I can write it as an integral from 0 to x of delta over L dx. And then after I've done that, I say, okay, essentially I've got u as a function of x is going to be equal to delta over L x plus some integration constant, because it's an indefinite kind of integral that I have. But if I know that at x equals to 0, the structure did not displace. So if I substitute here u for 0 is equals to 0, because that point did not move, the displacement there was 0, then essentially I can solve from that essentially c would be equal to 0. And now I've got a complete description for my displacement field. And there we have it. So these essentially derive by going from the solving for the equilibrium equations, relating what we've got from stress to strain by the material, something about what the structure is made of, getting our description for our strain. So in this case, it was a nice, simple description. It was essentially a constant over the structure. So the stress that is also constant over the structure. And then after I've gone through the integration, I've got my description for displacement. So this is the classical way. This is what you've learned sort of in MOW 227. This is sort of the approach, presume that you followed in terms of solving statically determined structures. Either if you were interested in the stress or if you were interested in how the structure displaced. Because in design, you always have two kind of states of designs, types of design. You've got what we typically call stress limited design. So this dominates typically when things break, or we have stiffness dominated design. So the stresses might be quite low, but the things are displacing quite a lot, and those displacements could be problematic. And then we want to essentially have an idea of how things displace. So that's essentially what we have. So if I can just maybe just wipe off here quickly, so I can put a summary down, and then I want to just do this process in reverse. And the reason I want to do that is I just want to equate now what's going to be the difference between this course and the classical kind of MOW 227 or structural mechanics course. In MOW 227, for instance, typically you solve the problems from equilibrium. Equilibrium equations. So just make sure I get another Koki. This Koki does not seem to write. Is it visible, if I can ask? Hope it's a lot better. Okay. So that's essentially from equilibrium equations. We could solve for the reaction forces. And this is now for statically determinate. So, and then from that, we could relate, we get the stresses out. Essentially, from the stresses, we could go to strain. We need something now about the material to do that. And then from the strain, we could go to the displacements. So that's essentially the sort of structural mechanics kind of workflow that we typically have. And what I just want to show you, what I'm going to do is I'm going to start at the displacement field now and work our way back. Because the reason is, in MKM, in this course, we're going to be applying the finite element method to approximate these functions. Essentially, if I have a good approximation, if I can guess what my displacement field is, like I've done here. Remember, I had to guess from the displacement field after I've observed what happened to the structure. Essentially, if I've got a good guess for the displacement field, I can go and check whether it satisfies the problem that I want. And so from a finite element point of view, from a FEM point of view, that's exactly what we're going to be doing. We're going to be guessing, not really guessing or approximating maybe, the displacement field. So let's just call it U of X for now. Okay, so just a quick interruption there. Okay, so we're going to be guessing or approximating the displacement field. And then essentially I can go from the displacement field and get the strain, which is also going to be a function of X. And then I can say, if I know something about the material, same as before, I can relate this back to stress. And then I can just check and make sure that the stress field is in equilibrium, or it's related to the problem that I want to try and solve. Okay, so that's really the focus, I'd say the core difference between the two courses when we approach the way we solve problems. In MOW 227, the workflow used to be, let's apply equilibrium equations directly, get the reaction forces, stress, strain, displacements. And the way we're going to be thinking about problems now in MKM 321 is we're going to be thinking it from the displacement point of view, get a good guess there, and then work our way back towards sort of equilibrium. So that's really what a big part of the difference is going to be, just philosophically thinking about the problem. Okay, so I just want to make sure I highlighted that. So what I'm going to do is I'm just going to wipe the board a bit clear, but then I'm going to say, let's start with this side of the problem. So this is the part that I want us to highlight now for this problem. Okay. So the problem is going to stay the same, still structurally determinate uniaxial bar. So let's just write that now. Still, this is a reminder that we're still solving the same problem. And what we have is essentially we have now our displacement field is delta over L x. Okay, so let me just wipe this off. And let's say either I've guessed this, or if this is my approximation to the problem, I want to just make sure that it's actually related to this problem, that it is indeed somehow related to what we see here. Okay, so what we can do is we can say, okay, let's compute the strain, so du dx, take the derivative of this, which is essentially delta over L. Okay, so that's a strain. So I can relate the strain to the stress by saying, just I can relate it via the material. So that's what this is. Let me just don't put a double bar on the, otherwise it gets confused with the matrix later on in the course. But essentially with the material that's known, I can relate it back to the stress. So I can say, okay, so it's essentially E delta over L. That is essentially how I get this now related to stress. And if I want to ask what is the sort of relationship between stress and sort of what I've expect to see in terms of being applied to the structure. I know essentially from, if I have applied a load P to the structure, I know that the stress would be essentially P over A. So that stress would be P over A for my traction that I've applied. I've applied a loading here of P, and it would result essentially in a certain stress state. And I've got a stress state that I've got from looking from my displacement side of the problem, and I want to make sure that that is related to essentially the stress state of what I've applied to the problem. So if I look at this value here, and I see what is the stress that I've computed, and it matches actually the stress based on what I would expect from seeing from the traction side of view, then these two problems match up. So if this quantity and this quantity is the same, then essentially this problem is related to each other. Obviously, if these quantities are different, then it's going to be a problem. So then it means the loading was different. It was not what I thought it was. So this is a way I can go and say, starting off from the problem of the displacement field, and then just knowing something about the material, I can essentially go and solve, well, I know everything about the problem essentially. So this is just important to understand again, from going for this route where I go from stress, strain, and then integrate it to get to displacements, and the boundary conditions come into play here. If I start off with the displacement field and I know something about the material, I essentially have full information about what's going on inside that material. And we just need to make sure that indeed, if somebody gives it to you, as opposed to you computing it, if somebody gives this to you, and they claim certain things about the problem, you just need to make sure the information is consistent. Okay, so hopefully this will give you a good idea of just a quick recap of what you've done in MOW 227 for statically determinate systems, and how we're going to be thinking about these problems in MKM 321. Okay, so this is just to make sure that I give you a good understanding that you can start also from the displacement and work your way back towards looking at what is the stress state and whether that stress state makes sense based on what is the loading on the structure. Okay, so let's go on to one more step. Let's complicate the problem slightly. Before I do, I just want to double check if there's any questions. Looks like everybody's quiet. Okay. Is everybody with me? Yes or no? Okay. Okay, I just want to ask, is this, the fact that this board is not 100% stable, that it's swaying a bit, is that the problem? Is that making anybody nauseous, or is it problematic if this thing is moving back and forth slightly? No? Okay, so that's good to know. Okay. Okay, so let's look at this next problem. So let's complicate the problem slightly, and now all of a sudden I'm going to take exactly the same problem. Again, a bar. But this time all I'm going to do is, I'm going to say let's, yes.
We can't really see there. It's too far on the left.
Is it too far on the left?
Yes. On well,
just make sure your screen's full screen, because I can see the whole thing.
Yes, because on my screen there's actually still a gap here. There's the edge of the board on my screen, so I'm not sure what's the difference.
Yeah,
now.
I can see the edge of the board by your finger.
Yeah.
Pin the video and then make sure it's full screen.
Thanks for that. Okay. All right, so let me just make this slightly bigger. It's just clearer. So the same problem essentially. Difference is now, and I just want to maybe just write down what we had from the previous problem. Essentially, we had the, for our problem here, point load P applied, length L, A, E. We essentially had and we had the delta. Okay, so those are just what we've had from the previous kind of example. I'm just putting it there in case we need to make reference to that. Okay, so essentially that is the problem that I want us to look at. And let's say we apply somewhere in the structure here, we apply a load P. Okay, so that's essentially a load P. And let's complicate it. Well, let's complicate the problem slightly. Or I don't know if you want to start with a more complicated problem or just start with the problem as is. But essentially, all of a sudden what I have here is I have, okay, let's start with this version. Actually, maybe I think we're gonna run out of time if I don't do the more complex version rather. So let's just make the structure immediately cut into two. Doesn't matter. Okay, I think I'm going to run out of time in any case. I see it's 11 past. Okay, so let's just stick to this version. I'll do the next one in the next lecture. Things are going slightly slower than I was hoping. Okay, so essentially, this is what I have. I've applied a load.
So I think your camera has been disconnected or something. We can't see anything.
You can't see anything. Oh,
yeah.
That's a problem. Let's check. All right, thanks for that. All right, is that better?
Yeah, we can see.
All right, thanks. Okay, so I've got the same problems what I've had here. The only difference is I'm applying the load somewhere in the middle, but I'm also clamping that right inside. So if I now look at the free body diagram of this problem, so let's say this is also length L. And let's say for argument's sake, I'm putting it somewhere at L0. This is where I'm applying the load. It's also made of material A, a cross-sectional surface area of A, and the Young's modulus of E. So that's sort of part of the properties of that structure. Okay. So essentially what I have here is I know that there's reaction forces here. So P is what I've applied to the structure here. But there's going to be a reaction force on this side, and there's going to be a reaction force on this side. So there's essentially a reaction force 1 and a reaction force 2. And if I want to try and solve this problem now from a normal static equilibrium equations, let's start with sum of forces in the x direction. What I get out is that R1 plus P plus R2 must be equal to 0. And from that, I can isolate and say P is equal to R1 minus R2. So that's essentially what I learned from that. From sum of forces in the y direction and sum of moments, I'm not going to learn anything else in the structure. Okay, so that's essentially where I am at this point in time. So what am I to do? So I need to have additional information. So I can't solve this problem as is. I need additional information. And there's various ways that one can invoke additional information. So for instance, one way one can invoke additional information is if we know something about L0, if it's in the middle, for instance, let's say it's L over 2, then it's easy to see that there's going to be some symmetry here. Because it's the same material throughout, it's the same cross-sectional area throughout. And then I can argue, okay, so these R1 and R2 unknowns are not quite completely independent. They should be the same in terms of the magnitudes because of the symmetry, if I wanted to exploit that. But all of these kinds of ways of thinking about the problem is all sort of exploiting in an unsystematic fashion things about the problem when you think about the problem. What we're going to do in this course is see to what extent we can solve these problems systematically. So just by following a kind of similar kind of reasoning process, by saying, okay, let's invoke something about the displacement of the structure into this equation and see what we learn. So essentially what we know is this point in the structure here, so it's going to be fixed. If I'm traverse up to this point here, which is now the distance, let's say L0, I can think of it as that point in the structure is now there, and if I apply that kind of a loading P there, it's going to be displacing that structure to some point to that side. Okay. If I then think about what's going to happen to this part of the structure here, it's going to just move, but there's going to be a wall here that's going to prevent it from moving, essentially. So what we can do is we can think about the problem as, okay, so let's think of the problem as a bar up to this point. So that this is a bar of L0, there's essentially loading being applied. I'm not 100% sure how the split is going to be of the reaction forces in general if this L0 is not in the middle, where I can exploit some symmetry arguments. I want to see what I recover if I follow some process in terms of what happens in terms of the solution. That's essentially what we would like to try and do. So if I follow this process and say to myself, essentially, if I think of this as one bar and this as another bar of the length of L minus L0, I can then just write down in terms of if I think of this bar extending and I think of this bar with each distance going further, that it needs to be pushed back a certain amount to be actually where the boundary condition says it should be, that the whole bar's length should stay L after it's been displaced. So I can follow that argument and then get sort of a set of equations out for what's going on. So I can say, let's start at essentially 0. If I want to move towards that point where the load is applied, that's L0. So let's just follow this argument. Essentially, there's going to be some loading, some reaction force. If I take the free body diagram of what's happening to this little bar, essentially, it's going to be, let's just maybe move this down slightly. Let's pull out the free body diagram of this bar, and let's pull out the free body diagram of this bar, if the two reaction forces are not the same. So essentially, I can think of it as, there's an R1 here. And there's that sort of loading that is applied there. So that's essentially one there. Actually, should actually just make sure I use my units of my directions properly. Because this is not actually, this could be problematic, I think. That's fine. Okay, let's just leave it at that for now. And essentially, I've got an R2 here, and I've got a R2. What I just want to do is depends on how we're going to think about this R, whether it's the magnitude, whether it's actually the loading. So at this stage, it's looking like it's just going to be translating this kind of bar this way, and this one is also just look like it's essentially going to be translating this bar. We can think about how we want to think about this R1. Is it just the magnitude that it represents, or is it actually including the direction? So I just want to make sure that I use it for now as the magnitude. Just for clarity's sake, because we're going to run out of time soon. So essentially, this one is under tension. So wrong way around. This one is under compression. Okay, so if I pull this bar here, this one is going to be putting in tension, and this one is going to be compressing. So that's essentially what I have. So I've got essentially loading in such a way, R1 is going to be the magnitude of the reaction force, which is going to put it into tension. And essentially here I'm going to have essentially the bar that's going to be under compression. And that is what I have. So what I want to know is, if I started off here, I'm started L0. And for this loading, the loading on this bar, this piece here, is essentially going to be loaded by R1. So that thing displaces then by R1. The length of this bar is L0 over AE. So equal plus. So that's what I have is I started at L0, set my distance is L0, that's there. I've now displaced that amount, so that's now the displacement amount, is now that additional displacement, I'm now somewhere there. Then I say, what is the distance of this bar? This bar's length is essentially L minus L0. So that is then plus L minus L0. Now I am essentially somewhere here. And what I need to make sure is that I need to make sure that this total length after it's disformed is actually still just L. So I need to make sure that this little bit that I've additional out here, what I have now is that this part is going to be in compression. So there's going to be subtraction of some displacement. The displacement is going to be P. Not P, it's going to be R2 L minus L0. That's the length of this bar. So that's R2 L minus L0. That's that length of that bar divided by AE. And this total distance here should be equal to just the length of the bar. So what I've just done is I've just followed a displacement loop of just saying, let's look at if I look at the deformed state and make sure that it stays the length L. So let's follow the argument again. Start at L0. So I go from here to here, get my additional displacement in tension, get my second bar's length, which is there, which is this brings me there, and then I need to subtract my displacement to make sure I get back to the point, and to make sure that that total length is essentially L. And this is additional information that I can bring in. So this is my additional equation. So what do I have? So essentially what I have is, I have for my sum of my forces, I say P is equal to minus R1 minus R2. So that's the first thing that I have. If I think of it from my reaction forces, I just want to make that sure that I'm thinking about this consistently, so that this and this are consistent. So let's just update this quickly. So essentially, if I want to write the sum of forces in the x direction this way and positive in that side, then I'm going to rather, so that will be still positive P, negative and negative. So that is essentially that. So make sure, if I think of it from a magnitude point of view. So what I'll do tomorrow is I'll just make sure that I think about this R1 a bit more clearly with you in terms of whether I want to think of it as the direction I impose, and R1 is the magnitude by thinking about the problem, or where I wanted that to follow. Okay, but the bottom line is there's the first equation from equilibrium that I have. And then the second equation is this additional equation that it tells me something about the length. And if I look at this, I can see that this L and this L will cancel out that L. And so this minus this must be equal to 0. So that's what I would get from that. Okay, so that is essentially where I'm going to stop for today. But what I'm setting off with is essentially, let me just write this down here before I stop completely. It's equal to 0. So what I have is equation 1 and equation 2, and my two unknowns. In this case are essentially R1 and R2. So I've got two equations, two unknowns. I can set up a small little system which is going to be essentially equal to P and 0 with my coefficients here for my little matrix system. And I can solve that and get R1 and R2. That allows me to do that. Okay. So the beauty of this is following this approach, all of a sudden, all of these problems become quite trivial. And what we'll do is we'll take this problem down with sort of a single bar. And then tomorrow we'll just extend it by saying, let's make this bar of different type of material, this one of different type of material, different cross-sectional areas, and generalize the problem. And just show you by following exactly the same strategy, following the same kind of pattern, we will still solve this problem. But now we've got a systematic approach to try and solve any of these statically indeterminate problems by saying we start off with the equilibrium equations, we apply and invoke the equilibrium equations, move on towards the sort of additional equation that we have. And that additional equation tells us something about how the thing is displacing. And all I did here is I completed a loop of how things were displaced. If I started somewhere and say, that's my distance L0, it's displaced, it takes me there. Now if I take the length of that bar, which is that, my structure would be there, but I know it should be there, so I need to make sure I subtract some displacement to make sure that it brings it back to that point there, that the total length of the bar stays essentially L. And now, depending on, doesn't matter where I put this force, where I apply this loading, this kind of formulation will allow me to solve for that and get sort of an idea of how the structure is loaded. Okay, so tomorrow what we'll do is we'll complete this and do a quick Python of that, update it in, just have a small introduction to how we would do this in Python, and then we'll just generalize the problem. And once that's done, we'll move over from little bars in 1D towards beams, and then we will continue on from there. Okay, I hope that was clear. Is there any questions from anyone's side at this point before we conclude?
Sorry, sir. I just want to find out, did we cut the bar at point where the force is active, at point where P is active? Yeah,
so here's P essentially. I've just said that let's imagine this distance is L0, where I apply the load P. So if that distance, the total bar's length is L, but if I apply the load at a distance L0, so L0 could be L over 2, it could be L over 4, it could be L over 8. It doesn't matter where I apply it. I can apply it somewhere. Then I apply that loading there.
So why do we lose the P in the force diagram in the additional information?
So it's not that we've lost it. It's still here. So the P is still featuring here in my reaction forces. But if I think about this bar here, I don't know how my reaction would split, how much of the reaction would split on this side and how much of the reaction would be on that side. Is that clear? So that I don't know up front. Depending on, like I mentioned, if my P is in the middle, I know that these two reaction forces would be the same because of symmetry. But if my P is applied somewhere here, and just from this argument here, you can see that the stiffness, it's going to be sort of a spring of a certain stiffness and a spring of a different stiffness. If you think about this stiffness argument, if L changes in the one bar versus the other bar and the rest stays the same, the stiffness is going to be the difference, yeah? And so essentially all I'm saying is that if you want to generalize the problem by having a L0 distance where I apply the load P, and I don't want to exploit any information, I want to see that it follows as a result, I can then just make sure I complete the loop by saying this is this free body diagram for this part of the bar, the part that is length of L0. This is the free body diagram of this part of the bar, the L minus L0. But what is important is if I sum these two reaction forces, that they indeed must sum up to P. If they don't sum up to P, I'm solving a different problem. So that's how that comes into play. Is that clear?
Not really, sir, but it's...
So R1, so if you look at this, R1 plus R2 is equal to P.
But so in your additional information, there's no P in any of the free body diagrams.
In this last equation, and this I completely agree with you. In this last equation, there's no P here, but it doesn't have to be there, because I'm solving these two simultaneous equations. So I'm not solving these equations independently. I'm solving them simultaneously, and P features in this first equation. So when I solve this matrix system, remember there's going to be values in here and here. So if you want to think about the value is going to be, it will be essentially something like 1 and a 1. And here it would be an R1 L0 over AE, R2 L minus L0 over AE. And this is a coupled system that I'm solving. So the reality is this information is going to be at the end, when I solve this, R1 plus R2 will be equal to P. Because it's the first equation that I'll solve. The second equation will make sure that the displacements are such that what this is displaced, that this displaced here, what this bar elongated, and what this one compressed are essentially the same. This is what this equation is telling me.
Oh, thank you, sir.
Is that clear?
Yes, sir. Thank
so
you.
maybe just if I can ask Mohammed, can you just ask this question tomorrow that I just clarify? But I'll in any case clarify this once we put it into a matrix equation. Because by putting it into a matrix equation, it's clear that this is the coupled system that we're going to be solving. And
Sorry,
it's not
sir, will we in the matrix system with R1 and R2 not drop out?
This is what I'm solving for. This is what I'm solving for.
No. In your first matrix, in the 2x2 matrix, will it not be LO over AE and then L minus what R1 and R2 not drop out in the 2x2 matrix?
So just
no, 2x2 matrix on your right hand, left hand side.
Sorry, what am I? Sorry, the R should not be here. My mistake. The R is multiplying with this. Yeah, that's my mistake. I just copied the whole term over, but it's not right. Yes. This is completely correct. This should just be L, and the R1 multiplies by that, and then essentially what we have is here, we have the L minus L0. Yeah, and it multiplies by R2. So I just copied this term over, but I should have dropped the R. Yeah, that's absolutely correct. Yeah. So this is the matrix system that I'm solving, and these are unknowns that I'm solving for. So it's L over AE, L minus LO. 0 over AE, and this is then the coupled system that I'll be solving for. Okay, so I hope that makes it clear.
Thank you, sir.
Cool. Okay. Yeah, I hope there's no other mistakes. Let's just double check. But anyway, so what I'll do tomorrow is I will maybe solve this problem in two ways. The one where we sort of infer the direction from reasoning, and the one where we don't infer the direction from reasoning, and see what follows. But I saw I was a little bit inconsistent here, so apologies for that. When I started drawing the Fibonacci diagrams, I didn't follow the same notation. Okay, so that wasn't too confusing, but for the rest, I hope the rest is clear. But the bottom line, what I just wanted to highlight is one equation from equilibrium, additional information, and all I did is I made sure that after things have displaced, that the thing stays the same length. This is really what this equation is telling us. All of these things, if I add them together, should be still the length of the bar. Okay, I'll see you guys tomorrow. Thank you for that. Okay, ciao.